And now we will consider the next topic, which is a sphere which is accelerating down a rough inclined plane. Since the inclined plane is rough, we know the ball is not only going to have linear acceleration, but it also is going to rotate, which means it is going to have angular acceleration as well. As you can see in this diagram, the ball is going to rotate in the clockwise direction. And how do we approach such questions? The steps remain the same. We will apply F net is equal to ma for the linear motion part of the sphere. We'll apply the net torque is I alpha for the rotational motion, and then we will connect the A with alpha. Linear acceleration and angular acceleration, the relation between them is A is equal to R alpha. And to solve the exam questions, it is important for us to apply all the three equations. So let's start with the analysis. For the linear motion, we will use F net is equal to m into A, but remember the concept F net is equal to ma needs to be applied along the direction of linear acceleration. Similarly, the second equation, the net torque is equal to I alpha. We will apply this about the center of the sphere. Now, remember, force is always a constant, but the value of torque will change depending on about which point are you finding the torque. So, torque value depends on the hinge point or the pivot point or the point about which we have to find the torque. And that is why when we are applying this equation, torque net is equal to I alpha, we can apply this equation along any point. But to solve the exam questions easily, it is better to apply the equation along the center of the sphere. I am going to explain this in a little while. As in, how will the calculations become simple if we are applying the equation about the center of the sphere? And finally, of course, we can balance forces in a direction perpendicular to the acceleration like we did in the previous case. So let's start with F net is equal to ma. So like in the previous case, the first force acting on the sphere is mg acting downwards. Then the sphere has a normal reaction which is perpendicular to the incline and going along this direction. And in this case, since the incline is rough, which means friction is there, in this case, since the sphere is sliding down, so the friction will act up the incline as shown in this diagram. And these are the only three forces acting on the sphere, basis which we have to identify the net force along the direction of acceleration. So like in the previous case, we will break mg into two components. So mg cos theta is the component perpendicular to the incline and mg sine theta is the component along the incline. In the previous case where there was no friction, the net force was only mg sine theta. In this case, the net force will be mg sine theta minus friction. And why are we subtracting? Because mg sine theta and the second force friction are acting in the opposite direction. So we'll have to subtract. So the net force will be mg sine theta minus f, and that we will equate with m into a. So mg sine theta minus f is ma, and from this equation, if we try to make A as the subject, so the linear acceleration A will come out as g sine theta minus f upon m. So this was step number one, applying the Newton's second law for linear motion. Now we will apply the Newton's second law for rotational motion, which is the net torque is equal to I alpha. Now remember the formula for torque. Torque is Rf sine theta. To identify the net torque, it is important for us to just check how many forces are there. In this case, there are three forces, N, mg, and friction. Since there are three forces, there will be three torques. What will be the torque due to normal reaction? We can apply the formula torque is Rf sine theta, but try to recall the basic concept. If there is a force which is passing through that point about which we are finding the torque, then the torque is zero. Let me repeat. If there is a force which is passing through the axis of rotation, then the torque of that force about the axis of rotation is zero. We have discussed this previously where I introduced the concept of torque. If you try to recall, we had discussed a particular example of a door. If you try to apply a force on the door which is passing through the hinges, if you try to push the hinges of the door, no matter how much effort you put in, the door is not going to rotate. That is because for the rotation to happen, torque needs to be there. But if you're applying the force which is passing through the hinge, then torque of that force will be zero, which means the door is not going to rotate. And the shortcut to remember that was if there is a force which is passing through the axis of rotation, torque of that force is zero. In this example, the axis of rotation is the center of the sphere. And here also I have mentioned that this equation is being applied about the center of the sphere. In the free body diagram, we can see that there are two forces, mg and normal reaction, both of which are passing through the center of the sphere, which means both these torques will be zero. Hence, we can write the torque due to the normal reaction will always be zero, and the torque due to mg will also be zero. So two forces are accounted for, but there is a third force, friction. That friction does not pass through the center of the sphere. So the torque of friction is definitely non-zero. And for that, we can apply the formula Rf sine theta, where F is the friction, R will be this distance, the distance between the center of the sphere and this point about which friction is being applied. This distance is the radius of the sphere. And theta is the angle between the radius and the friction, and that angle is 90 degrees. Hence, we can write the torque due to friction will be F R sine 90. The value of sine 90 we know is 1. So the torque due to friction will be F into R, where R is the radius of the sphere. And now we can apply the equation. The net torque is equal to I into alpha. The net torque will be 0 plus F into R. We are going to add all the torques. But if you remember, torque is a vector quantity. It not only has a magnitude, but it also has a direction. So in this case, since the sphere is moving in a clockwise direction, it is rolling, it is rotating in a clockwise direction. That means that the direction of torque due to friction is also clockwise. Now, ideally, we have to consider the direction into account. But here, since only one non-zero torque is there, we can ignore the direction. So the net torque acting on the sphere will be F into R. So let's apply the equation. Torque net is equal to I alpha. The net torque is Fr. So we write Fr is equal to I into alpha. And now we come to that third equation. Remember the relation between the linear acceleration and angular acceleration? So if we make alpha as the subject from this equation, we will get alpha is equal to A upon R, which we can replace in this equation over here. So the expression will become Fr is equal to I into alpha is replaced with A upon R. And now if we make friction as the subject, we will get F is equal to I into A upon R square. And after this, what we will do is we will put this value of friction into the equation which we had found earlier. We will replace this F value from the expression which was derived using the torque net is equal to I alpha. So now we will replace this expression of F into this equation. But before we do that, let us also discuss this. We had discussed the forces needs to be balanced in a direction which is perpendicular to acceleration. So just like in the previous case, here also normal reaction and mg cos theta will have to cancel out because both of these forces are acting perpendicular to the incline. So n and mg cos theta will be equal. This is supposed to be used in some exam questions. Now back to the concept. Remember what we are trying to do. We are trying to identify the acceleration of the sphere which is sliding down a rough inclined plane. We already got one expression of acceleration, but now we are replacing the expression for friction. Friction will be IA upon R square. So let's replace the value of friction using IA upon R square. So the expression will become G sine theta minus F is replaced by this expression IA upon R square divided by M. If we simplify this, we'll get G sine theta minus IA by MR square. Now remember, we have to find the acceleration. So we have acceleration on the left, also on the right hand side. So we need to make acceleration as the subject. So we will take this entire term which is in negative and we will put that on the left hand side. So the expression will become A plus IA upon MR square is equal to G sine theta. We have to make A as the subject. Now both of these terms have A in it. So we will take A as common and the rest of the terms will go in the bracket. So we will get 1 plus I upon mr square in the bracket and A is common. On the right hand side, we have G sine theta. If we simplify this bracket by taking the LCM, we will get mr square plus I divided by mr square in the bracket. So mr square is the LCM and the numerator is this. And now if we try to make acceleration as the subject, so mr square will go in the numerator and mr square plus I will go in the denominator of the right hand side. Hence, A will be equal to mr square g sine theta divided by mr square plus I. This is the expression of acceleration which we required. But if you try to recall the previous case where the inclined plane was smooth, the linear acceleration in that case was A was g sine theta. Let us try to compare that value with this expression which we have gotten because g sine theta also exists in the numerator. So how do we simplify this expression? Since we have mr square in the numerator, we are going to divide the numerator with mr square so that mr square gets cancelled out. But we also need to divide the denominator with the same number, mr square. So what we have done, we have divided the numerator and denominator with the same number, which is mr square. But this mr square will get cancelled out with this mr square because that is what we wanted to do, so that g sine theta becomes the numerator. And in the denominator, we have mr square plus I divided by mr square. That can be broken down as, we will write mr square divided by mr square plus I upon mr square. So what we have done, we have tried to break the denominator into two terms. And again, mr square will get cancelled out. We will get a 1. So the final expression for linear acceleration will look like this. G sine theta is in the numerator, and in the denominator we have 1 plus I upon mr square, where I stands for the moment of inertia. And please be careful. I have observed that while the students write down this expression, they replace I with fun. So by mistake, students write a 1 instead of an I. So just be careful about that aspect. And this is how we find the linear acceleration of a sphere which is sliding down a rough inclined plane. And in case the question asks us to find the angular acceleration, all we need to do is just apply the formula A is equal to R alpha. So the expression for A we have already gotten. All we need to do is just divide this expression with R to get the angular acceleration. And now let us quickly summarize what we have discussed so far. Acceleration of a sphere sliding down an inclined plane. We are going to consider two cases. The first case is when the incline is smooth, where we saw the acceleration of the sphere was g sine theta. Case number two, when the incline is rough, in that case, the acceleration is g sine theta divided by 1 plus I upon mr square. And in the exam questions, all you need to focus on is, does the incline have friction or not? Depending on that, the expression for acceleration will change. Because the moment friction comes into the picture, the sphere will also start to rotate. And once the rotation starts, moment of inertia will come into the picture.